1.5 is titled Limits Involving Infinity. We've seen a few of these things happen already, but we haven't formally defined what's going on. And there's some pieces in what we're going to see today that we haven't seen happen yet at all either. So we're going to start with a basic graph that you have seen, and we just talked about it in section 1.4 as well. The rational equation 1 over x. Do you remember what this graph looks like? Could you sketch it? Go for it. Sketch it. I'm going to sketch it. You're going to sketch it. We're all going to have a sketch on our paper. Okay? So your sketch should look something like this. Does it? Now, when we talk about this graph, for the very first time when you encountered it, it was somewhere in an algebra class. Maybe Algebra 2 would probably be where you saw it, and in high school. And we talk about this graph as having two asymptotes. If you remember, we sort of can loosely define asymptotes as these lines that we get really, really close to on the edge of something. You know, as we get really nearby something, we don't actually usually touch them. Occasionally we do. They're sort of the weird scenarios, but normally it's something we get very, very close to and don't touch. Which starts to sound an awful lot like a limit, doesn't it? It's kind of how I defined limit when we first started, is this value that we get really, really close to and we may or may not touch. So that language already sounds a little bit the same. In particular on this one, we have a vertical asymptote. It's at the y-axis. And we have a horizontal asymptote that's actually the x-axis, right? That's what we're seeing happen. So now what with that? Well, we're going to take a look at that, and we're going to talk about finding those asymptotes, because those asymptotes are actually related to limits. So let's take a look at that. We're going to consider finding the limit as x approaches 0 from the right. So you have that little plus sign. One way that we could describe this is we could say that the limit doesn't exist. Okay, so why might we say that? Well, because it actually doesn't get close to any particular number. It goes up forever. So over here, my picture, my image, I know you all are writing, but just bear with me. My image as I'm approaching x equals 0 from the right-hand side is that I'm going to infinity, right? And so sometimes you will see the language that this limit doesn't exist because it doesn't stop. Now, that's okay. There's nothing wrong with that, but limits cannot exist in lots of ways. They cannot exist because there's a jump in a graph. They cannot exist because there's a hole in the graph. They cannot exist because an asymptote. So just saying that something doesn't exist doesn't really provide a lot of information. One could also say that the limit's infinity, which is how we've sort of talked about it up till now. And the reason we have is because when we say that the limit is infinity, it gives us more information about the fact that it doesn't technically have a value that it's approaching, but now we know what is happening there instead. We know it's getting infinitely large. All right, so in particular, we're going to use that language. If it gets infinitely large or infinitely small, we are going to use the infinity and negative infinity values instead of saying does not exist. Categorically, that gives us way too many sort of outs. So we're going to be much more specific. So in particular, we're going to talk about finding asymptotes. First, we're going to talk about finding vertical asymptotes. So you'll remember this as we go through. This is nothing new. This is algebra. Okay, this is not calculus. Finding asymptotes. The first one, vertical asymptotes. And I'm doing this specifically for rational functions. Okay, so there's other possibilities of how to find asymptotes. Specifically, we're looking at rational functions. So the first thing you do is you reduce the rational expression to simplest form. So if it has the ability to be factored and simplified, you have to factor and simplify first. Okay, if you don't, then you're probably going to end up giving me an answer of something that's an asymptote that you think is an asymptote, and it's not. It's a hole in the graph because you didn't reduce it first. So you have to reduce first. And then the second thing is once it's reduced, you set the denominator equal to 0 and you solve. Okay? And that's kind of what we were looking at when we looked at limits already, right? It's not an accident. That's really what's going on. But it starts to feel like, didn't we already do this? And the answer is yes. So bear with me. This part we haven't done yet. This is finding horizontal asymptotes, again, for rational functions. There are 3 cases. And this is where if you've printed out your notes, you're in good shape because you have so much less to write down. Here are the 3 cases. The cases have to do with the degree of the numerator and the denominator. Degree of the numerator, degree of the numerator. You see that phrase in there on all three cases. Do you remember what degree means? I don't mean like temperature, right? Powers, exponents, yeah. So when we're talking about rational functions, we're talking about functions that have exponents. And if they don't actually see an exponent, it's an exponent of 1 or 0, something like that, depending on the function. So we're looking at something that may look maybe like, I don't have any written down, x squared plus 1 over x minus 2, or something like that. A polynomial on top, polynomial on bottom, and I maybe have exponents on top or bottom. Okay? Now, I don't write this beside case 1 to say that this is case 1. Is it? It is, actually. Case number 1 says the degree of the numerator is greater than the degree of the denominator. And that's exactly what happened on this particular one, isn't it? The degree of the numerator here is what? 2. The degree of the denominator is? 1. Good. So this is actually the first case. If I turned this fraction upside down, I would be case 2. I'd have x minus 2 over x squared plus 1. So this would be the case where the degree of the numerator is smaller than the degree of the denominator. So on the first case, if the degree of the numerator is bigger, there is no horizontal asymptote. If the degree of the denominator is bigger, on case 2, we do have a horizontal asymptote, and it's x equals 0. And if you take a look over here at this function right here, this is case number 2. What's the degree of the numerator? 0. The degree of the numerator is 0. You might think, okay, like why? Just because there's a number up there? Well, kind of. Remember, the number 1 is really just the same as x to a power of 0. That's why we say it has an exponent of 0. It's because we can think of it that way. So yeah, the numerator actually has a degree of 0. The denominator has a degree of 1, right? 1. And you'll notice that the horizontal asymptote actually is the x-axis, and the x-axis is the equation y equals 0, right? So that actually is a good picture of case number 2. Case number 3 sounds like it's the most complicated thing to write down. It is so easy, but there's just no easy way to write it. Maybe there's things in your life that are like that too, where like that this makes perfect sense, but I cannot explain it to you in a way that's going to make any sense. That's kind of what this looks like. This is saying the degree on top and bottom are the same. So let's say, for instance, we had the x squared minus 2 on top, and let's say we had 3x squared plus 1 on bottom. So the degree is the same on top and bottom, right? All that this is saying is that we look at the coefficients of the highest degree term, and while there's technically not a number in front of x squared, we know there is. It's the number 1. And it's saying that those numbers that are in front are the actual asymptote. So it's y equals 1/3. So it's not hard. It just is the most awkward thing in the world to write down. So you look at the ratio of those leading coefficients for the highest degree term. Does this all look familiar? I know you've seen these things before because these are taught in algebra when you deal with rational functions. That means it may have been a while. I recognize that too. But vaguely, this is sort of something we've seen before, right? Okay, fabulous. Okay, I want to do one example and then we'll stop right before we talk about the other type of asymptote, and we'll pick up with that one next time. All right, so here's my function. And the directions, and this is why I wanted to get to this, actually have some interesting language that we haven't seen before. They say, determine all horizontal vertical asymptotes. Okay, that was my last 2 slides, so we talked about how we do that. But then it says, for each vertical asymptote, determine whether f of x approaches infinity or f of x approaches negative infinity on either side of the asymptote, and that looks a little funny. We haven't seen those directions yet. So I want to get to that point too. All right, so let's first look at this issue of horizontal vertical asymptotes, okay? And I'm going to do them out of order simply because I wrote them in the opposite order when I wrote the notes for them before. I talked about vertical asymptotes first. So let's actually do vertical asymptotes first. So looking back at the descriptions for how we find vertical asymptotes, what did it say I need to do first? Reduce if I can. How do I know if I can reduce? What was that? No, say it louder. I just didn't hear.
0 over 0?
If you have a 0 over 0, but then you actually have to know what number to plug in, right? And I don't have a number here in this case. Sometimes I do. I don't on this one. We can factor to see if there's any factors that would reduce, which would take care of a 0 over 0 possibility. That's exactly where that would come into play. And regardless, we're going to have to factor at some point anyway. So we're going to factor. Let's think about that numerator. Does the numerator factor? No. Do you remember why? There's a couple of reasons looking at it. You think, oh, it's not going to factor. Okay, I'm hearing a couple things. What did you say? Somebody back in here. Was it you, Cooper? Okay, it's not a trinomial. It doesn't have 3 terms, so I don't have an x squared, an x, and a linear term, a constant term. What did you have in mind? There's not a power of 2. I think you mean like on the number 1 at the end. Is that what you're thinking? That can also be a clue, but there's something else that's causing this to be even worse of a red flag than either of those. Those 2 things are good, but there's something else too. Not that one. I'm just talking about the numerator right now, just the top. The 3 at the front will tell us that there's not the ability to cancel something potentially, which is what you're thinking of. The plus sign in between. If this were a minus sign in between, we could factor the numerator because we could have the ability to factor it as a difference of squares. I mean, we could. It would be awkward and it would look weird and it would be completely unhelpful. But if it were a subtraction sign between, we might have the ability to factor. But the fact that it's an addition of things, that with some squareds involved, that's going to rule those things out. Okay? We saw that happen a couple class periods ago. Do you remember that? Where we had a difference of squares on one case and I did a sum of squares on the other? Yeah, so this sum of squares, or the sum of the ability to write it as squares is causing problems. I can factor the denominator, however, so the numerator is going to stay put. What in the world will the denominator factor into? Okay, does everybody agree with that? X minus 3 and x plus 1. Okay, so it doesn't have the ability to reduce. That's fine. So what's the second step that I have to do then to find vertical asymptotes? Set the denominator equal to 0 and solve. Fabulous. Okay, so the denominator is already in factored form. That's nice. What does that mean I need to do? Denominator equal to 0. And I need to solve this, right? Now, whether or not you need to see this written out in detail, I'll write it down this one time. The 0 product principle says that if 2 things multiplied together are equal to 0, one of them must have been 0 to start with. So either x minus 3 is equal to 0 or x plus 1 is equal to 0, which gives me x equals what? 3, and x equals negative 1. Notice, my answer is not 3 and negative 1. My answer is x equals 3, x equals negative 1. You might be thinking, why does it matter? Well, it matters because these are asymptotes, and asymptotes are lines. And lines have equations that say either x equals something or y equals something. They're not numbers. So be really careful about that. The tendency is to just spit out a number, and these are not numbers, these are lines. Okay? So there's my vertical asymptote. Horizontal asymptote. Can you tell me which case we are in? Are we in case 1, case 2, or case 3?
Case 3.
Case 3. How do you know? The degrees, the powers are the same, right? They're both degree 2. So I'm in case 3, which means I do what? Yeah, I look at the coefficients of the highest degree term. Okay, so now, again, this is a line, so it needs to say either x equals or y equals. Which one is it? It's y equals, because this is a horizontal line. Y equals 3. Again, 3 over 1, which reduces to 3. Now, a graph would help with this if you want to be able to answer the other questions. You could also think about what's happening in terms of like numbers to put it into a table. The last thing that we're supposed to do is we're supposed to decide if f of x approaches infinity or if f of x approaches negative infinity. On either side of the asymptote, and this asymptote that it's referring to is the vertical asymptote. And we have 2 vertical asymptotes, which means I'm going to write down 4 pieces of information. Okay? What 4 pieces of information? Well, the limits from either side. So I need to find the limit as x approaches 3 from the left of my function. Make sure the f of x is there. The limit as x approaches 3 from the right of my function. I need the limit of f of x as x approaches -1 from the left, and the limit of f of x as x approaches -1 from the right. There are 4 pieces of information that I need. And let's go ahead, take your calculator out, because your calculator is a great resource in being able to answer the question that's being proposed right now. I don't actually have this one drawn for some reason on my paper. So here's -1, and here's 3. So I have a calculator nearby. If you do a zoom, just a standard window, zoom 6 is a decent view on this one. You get a picture that looks something like the following. Obviously, I'm drawing in arrows that your calculator doesn't draw in, but does yours look something like that? Does anybody's not look like this? Okay. So let's take a look at each one of these, and I'll just do in the order that I've listed them. Let's start with this one right here, which is limit as x approaches 3 from the left. So here's 3, and this is the left-hand side of it, right? I mean, correct? So if we're tracing along this curve, we're going to be tracing along down like this. What value are we approaching? You got it, -infinity. So my first answer on these limits is that I'm going to -infinity because I'm tracing along the line, the curve, towards x equals 3 from the left, and I'm going down. This one right here underneath it is 3 from the right. So this is 3, this is on the right-hand side of 3. So I need to be getting close to the 3 value from this side, so I'm going to be tracing along the pink curve, and in this case it looks like this. What's that limit? That's infinity. Notice the signs make a big difference, so make sure you get the sign correct on what you're trying to say. All right, this next one is approaching -1 from the left. Here's -1. This is the left. So I'm supposed to be on the pink curve over here, because this is to the left side of -1, and I'm getting close to -1. What's happening? That one's infinity. And then I'm supposed to be approaching -1 from the right. So again, here's -1. This is the right-hand side of that. So I'm tracing along the pink curve, going towards -1, and coming down here. One's -infinity. Does that make sense? Okay, we actually have about 5 minutes, so I think I have time to show you the slant asymptotes, and then we'll stop after that one. That'll be a good spot. I didn't think I'd get that far. All right, slant asymptotes. Do you remember that one? You may have heard them called oblique, slant or oblique to asymptotes. What they are is instead of being horizontal or vertical, they're at an angle. They're slanted. Slant asymptotes happen in one and only one case. They happen when the degree of the numerator is exactly 1 bigger than the degree of the denominator. So 2 bigger doesn't work. And if it's the same, of course, we have that scenario before, but if it's exactly 1 bigger, then we have something called a slant asymptote. And the way that we find this is we find a slant asymptote is we use long division with polynomials. So let me just remind you, and this sounds sort of silly, but once we do long division with polynomials, sometimes people get a little bit freaked out. It's really just like long division with whole numbers. So for instance, if you had the number 40 and you're dividing by 3, you ask yourself something like this. How many times does 3 go into 4? And you say, oh, it goes in 1 time. And then you say 1 times 3 is 3. And then you subtract. And you say 4 minus 3 is 1. And then I bring down a 0. And I do the same thing. How many times does 3 go into 10? Oh, 3 times. And then 3 times 3 is 9. And then I subtract. And I get a remainder of 1. This is what we would call the quotient. And in our case, that's where we're going to find the slant asymptote. So let's do it with polynomials so that we can mirror this sort of a scenario with how that works with polynomials. This one says to determine all vertical and slant asymptotes. Now, vertical we've done before. The numerator doesn't factor. Why? It's not a difference. It's got a plus sign in between. So you guys were paying attention. That's like star for the day. So well done. Star for the day. Okay, so the vertical asymptote will just be the denominator now since the numerator doesn't factor, right? So I set the denominator equal to 0. So where is my vertical asymptote? X equals 2. And you even said X equals double star. Well done. X equals to 2. Good job. All right, slant asymptote. Does this one have a slant asymptote? Yes, it does. How do I know? The degree on top is exactly 1 bigger than on bottom, right? 2 on top, 1 on bottom. So let's actually do the long division that I was wanting to get to so you can see that. All right, so whatever's on bottom goes on the outside. That's x minus 2. Underneath the division sign, we're going to put the x squared plus 1, but we're going to do it a little bit different than what you see. I'm going to put x squared plus, 0x plus 1. It's just a placeholder. It's like if you have the number 1002, you don't put a 1 and a 2. You put the zeros in between to represent the hundreds place and the tens place where you have nothing. That's what you're doing. This is just a placeholder, 0x. And you do the same thing that you do with numbers. You look at the first number here, in this case it's an x, and you look at the first quantity here, x squared, and you ask yourselves how many x's go into x squared?
2.
2 of them, but that's not really what you meant, right? Not 2. X of them go into x squared. Another way of asking it, which is a little bit more, helpful maybe, is to say something like, what do I have to multiply x by to get x squared? And that's x. That feels a little bit more natural. So I need to multiply x by x to get x squared. So I take what's on top, the pink, and I'm multiplying it now on the outside. X times x is the x squared. And then x times negative 2 is negative 2x. And you can see now why I have the placeholder 0x in there, right? I want them to line up. Okay, come back over here and tell me, what did I do after I wrote down my 3? I subtracted. Okay, well, I'm going to subtract here as well, but subtraction is simply changing signs of whatever I've got. That's what subtraction does. It reverses whatever signs that I had. So in this case, the x squareds, of course, add to 0. And then I've got 0x and 2x, so that's 2x. And then the next thing I did is I pulled over here. I pulled my 0 down, right? Well, I'm going to pull my 1 down here, and I'm going to do the same thing before. And I'm almost done. Let's take like 1 more minute. What do I have to multiply x by to get 2x? 2. Yes?
Why is it x squared?
Because x times x means x squared. That's what squaring means, is something multiplied by itself. Maybe let's check on the after class, because I maybe don't understand your question. Okay. I've got 2, so if 2 times x is 2x, 2 times negative 2 is negative 4. And then what do? I subtract. So that means I change my signs. 2x and negative 2x is 0. 1 plus 4 is 5. 5 at the bottom is the remainder, which doesn't actually affect my answer to the question. My answer to my question is right here. My slant asymptote, but don't just tell me my slant asymptote is x plus 2. Very good. It's a line, y equals, and in this case it's y equals x plus 2. Lines always say y equals or x equals. So we get a slant asymptote of y equals x plus 2.